Hello everyone. I am Pratyush Ranjan, a final year undergraduate student at IIT Bombay, and I would like to discuss today with you about something introductory to ML and why ML is dominating everywhere, why you should pursue it, what are some of the myths or traps which you should avoid at the beginning level itself so that you can learn deeper and uh, learn it in a smarter fashion. So today we will be discussing just about why ML is everywhere, as you can see in the first page itself. And then we would be answering some of the questions like how you can learn ML, what are some of the common beginner mistakes, then what is ML exactly, how it is different from other primarily used methods nowadays. So without any further delay, let's start the topic. So first, I would like to answer the question, why is ML everywhere? So as you can see, there are various points. These are some of the prominent points which I got. Otherwise, you can, when you try to observe here and there, you will find more points. These are some of the points which I extracted just for the sake of illustration. So you can see that uh, machine learning exploded because of three causes, like computing power drastically increased since the time of 2015 and all. You will be surprised to know that even though algorithms existed earlier for some of the tasks, like if you go deeper into the architecture, there are some encoder decoder architecture, RNNs, LSTMs, which for the time being you can understand it to be a sequential algorithm. This was discovered as early as 1997 or so, but we saw its application somewhere after 2006 or 7 by the advent of relevant hardware. So you can clearly find out on deeper research that with the computing power increase, these it made us capable enough to test the algorithms which are already there, found out by various researchers. Then also the companies tried to gather some of the data for their own analysis. Like clearly we started generating massive amounts of data through clicks, searches, transaction, and many more applications. And also parallelly, some new algorithms, or you can say architectures of machine learning, were also trying to develop. One of the key and you can say innovative one was transformers. And based on this only, you can see today's GPT and all. The full form translates out to be generative pre-trained transformer. This architecture was capable enough to, you can say, mm, generate some of the natural language natural language sentences when a query was passed into it. And clearly ChatGPT and all are just, you can say, some more modifications or advancements into the existing GPT architecture. And clearly some of the tradition traditional software struggle when you are having too many edge cases for humans to enumerate. Like in backend architecture and all, you might have to write too many things to just get a model or solution working. Then there is a rapid environment change, fraud tactics, as you can say. Clearly, the fraudsters are finding out hundreds of ways to crack into the system. So we have to detect that quickly. And here, rule-based logic won't work. Rule-based logic here clearly will not work. And scale of the data is beyond what one can imagine. for these number of users, you have many of the events occurring with them. So here, classic rule-based writing, or you can say even software development, will not work in decision making. And if clearly it has been observed by many mathematicians or rather firms like IBM that if you have a data and you want to solve a task, you can often learn some behavior from the existing data. Sorry for the glitch. Like the date, this is just a 2D data. You can assume it to be any n-dimensional data or some data which have n number of features, and analyzing those n number of features will clearly help in ma managing, predicting, or rather deciding what actions to perform next. Now, coming on to the answering of questions as to why you should learn ML, because MLAI roles are, as you can see, are some of the fastest growing careers, and like the software development role in every company nowadays, it has crept into every big firms, and even startups are looking for the roles in data science, machine learning, and all. It finds its application in almost any of the company. And you can also see the trends of, you can say, AI based startups are getting funds more easily because they assume that the AI is booming nowadays. I would say it is just like a dot com bubble where everyone was just chasing the dot com thing, and then it suddenly burst, as you might recall from past. Similar will happen with the ML, and as you can also see, after the dot com bubble burst, dot com became so normalized that it became one of the core skills to be present in a company. Similar will happen with ML. I would say that bubble burst of AI would be seen as a transition, but I would clearly say that adaptive learning is the thing you should be focusing on. Adaptive learning, like now it's machine learning, and clearly when this normalizes, you need to get specialized into skill, as many of the people are learning it nowadays. Learning for now is fast because for the time being it's future proof. As you can see, software that doesn't use data by is getting replaced. Like even in software development, many of the models are related to, like in SD also, we integrate some of the ML models to take decisions and perform tasks. You can also see ML literacy will be soon a basic for developers as to if he or she knows how to use a database. And once you know the generic approaches of ML, like going with data pre-processing, understanding the business problem, then finding the right model which can solve your use case. Sorry for the glitch, guys. It's very likely happening because I'm writing on the PDF itself, which can solve our problem. Then you can say uh, iterative development happens. Iterative development, as in any product development. These, I would say, these are some of the things where you should look on to why you should learn ML. And also there are various applications and various motivations you can find out why you are learning ML. And as I discussed earlier, that there are various things where ML comes into daily use. Some of the examples include like Netflix recommendation engine. So as you can see, there are various applications where ML is used in day-to-day life. Some of the applications are clearly the recommendation engines. Like how are you able to get engaged so much in contents of YouTube, Insta, Netflix, and various other streaming platforms or social media platforms? They uses a simple idea of recommendation engine where again the data is a very important thing to look after. In the thing, what they store is what what you watch, what you watch multiple times, what similar type of people like you enjoyed, how you rate something, like based on ratings also they try to present the content or not present clearly. If you rate something poor, the next time you won't see it very likely. Apart from capturing these, there are various other, you can say, engineered or thought of things which they try to capture whenever you watch a show on Netflix or any other platform. Some latent preferences are also captured, like something never labeled by UI. Generics are, of course, labeled in the Netflix UI, like crime, horror, comedy, but some latent things like this descriptive thing, some slow crime drama with female leads having strong role play in that. Under the hood, it tries to do collaborative filtering. I would not go into the depth of how these models work because it would otherwise make the things too long to watch. People with similar persona liked some X content. It's very likely you will also like it. So it's called as collaborative filtering. Content-based models as you watch multiple times some genre, cast, movies of a particular director. These things are clearly recorded, and then you are presented with a content-based model by filtering the genre and all. Then ranking is done accordingly out of the hundred of movies appearing by the above two filters. You get some most relevant ones, maybe by popularity or some genre which you like the most. Clearly, you can see here then that for each user itself, there are many of the data points or rather rules which has to be written manually, and you can't hand code it perfectly. So you will be needing machine learning which can continuously adapt into the behavior of user, how user sees something, and this generic algorithm will work for all the users accordingly. Second application is clearly the Google search. It tries to optimize its search pages by using machine learning indirectly. Like you can see some of the example, query intent we type Python, what to present first, should we present snake or language? Very likely if Python is trending as a language, then the Google will likely present the Python as a programming language as a first page. Programming language will appear, and on the, you can say, second page or list, your snake wala definition will appear again. And clearly Google again learns from the behavior. If user keeps skipping some result and click the result continuously, then after some time other users will be presented first with the third page or third search result. And based on this, dynamically, Google tries to re-rank its pages. It combines these types of signals like text relevance, page quality, personalization, and all. Earlier, ranking was designed basically by, you can say, manual signals like most frequently visited, most frequently visited, rating of the web page, matlab rating of the content which is being visited. These were some of the hand-based rules. But as you can see, based on your personal preference, it will rank the things accordingly. And it's not like for every user you will have to hard code some of the things. These will be taken care of by a generic ML algorithm itself. Another application is it as to face unlock. So here are the steps listed, like when you set up face unlock, face captures multiple images. Like you set up a face lock and it will try to capture your face under different lighting conditions or possibly by tilting your face sideways like that. A deep neural network is basically going on in doing it where the each of the image of yours is converted into a vector embedding. As a matter of fact, vector embedding concept is very popular in NLP based tasks also. So the concept of vector embedding is like clearly in the datas like images or text, you cannot pass directly in it into the machine because machine understands only numbers. It it would not understand the things like text, image, or any other data type which you pass. And also based on the numbers only, it will try to compute similarities, 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 and then deep models are developed based on these numbers or embeddings itself. Embedding you can understand just as a dimensional representation. Like supposing there is a sentence, I love bananas. So basically, these type of sentences will be broken down into a representation of vectors. Some number will be there, 0.6, 0.8. Matlab, I am just writing this for illustration. Otherwise, whatever research paper or rather when you try to work with the embedding models, typically they use a embedding with 512 dimensions, which represents these type of 512 numbers. And you can say each of these 512 numbers represents some aspect of the sentence. Like I can say here that I love bananas in if zero point 0.5 is written, then zero point 0.5 might refer to the fruit attribute of the bananas. In apple also, in apple, like apple can be considered as a company or a fruit again. So these embedding models also are able to distinguish between what is fruit and when it is referred as being company. Clearly, we have some pre-trained or rather available embedding models which are trained on a large number of these type of sentences, words, or you can say document corpus available throughout the internet so that the embedding models generated by using the dataset are such that it can capture almost any of the, you can say, semantic or hidden representation of what a word or a rather sentence represents. These were just the idea of vector embeddings and its functionality. Similar can be done while using the images. Image also consists of embeddings as to how are the textures, how are the eyelashes, structure of nose, and various other things. At unlock time, clearly you can see the camera captures your face, then the network generates an embeddings, and the embeddings are compared based on the distance. Distance is again a similarity measure, like there are various similarity measures. One of them is distance based, another is cosine similarity. These are some of the, you can say, easy to understand and rather intuitive similarity matrices used in the ML. And again, here you can see that the key here is no one coded. Distance between eyes must be X or mouth shape must be Y, something like that. Each of these features, like one of the features of our embedding model representing eyes distance, some might represent the mouth shape, and similarly, there will be features in that vector embedding. I hope you are able to understand how embedding tries to capture our, you can say, real life data of text and images into something which machine can again understand and compute on it to find out the relevant results. See, as you can also see, humans couldn't realistic encode these things as rule, and ML can really learn these visual patterns in a more robust manner. Again, one of the common things where ML is used daily is on fraud detection. Many of the banks and payment processors like in our country, NPCI, Razorpay, all of these are using some, you can say, sophisticated ML models to detect the frauds. And I will show you later that the fraud detection is one of the most challenging tasks in this industry because even fraud, mat- supposing there are 1 million users, even a fraud happening with hundreds of them would be a very negative impression on the overall company. Negative impression on overall company. These are some of the steps, or you can say points, which are taken care of while using a fraud detection algorithms. ML models clearly learn normal patterns of user and merchant transaction, like its habits, ranges, geographic patterns, and if any anomaly or some, you can say, dissimilarity is found, then these models clearly rate those things as a fraud detection. Similar application is of spam detection model. Like spam detection is also working in a similar fashion. And again, model keeps retraining itself and updating with newly confirmed fraud and non-fraud cases. These rule-based things will generate tons of false alarm as fraud cannot happen in one of the ways. There can be multiple reasons for occurrence of a fraud, and we have to check into all of it. And we clearly cannot hard code it for a particular user at a particular location. If someone is poor, he does not transact much, and supposing his transaction count increases rapidly 1 day or 2 day, then clearly some fraud is occurring with that user, and we might check into that user particularly. And supposing someone is at a managerial position on bank or managing multiple accounts, then within that single account, many transactions happen, and for that user and for that case, clearly we cannot tag it as something which is fraud. Then ChatGPT, as you might have been using, it's literally used by almost every company employee, students, and all. Once a model is large enough, clearly you can see that it is able to write codes also, though it's not correct clearly, but it provides you with a baseline level which can be improved upon by you. And as I have stated earlier, it is trained on a massive text corpora, or you can say collection, to just predict the next token, like next word which is there. Since the text data is massive, it is able to answer a large number of questions across many domains. Then rule-based programming comes under traditional programming, as I have been repeatedly emphasizing that you cannot cover every corner case. Every day new corner cases arises and one cannot identify it, while the machine learning can identify it by continuous learning on the new training data which it gets from things like user transaction, how user behave on a particular platform, and like that. These are some of the limitations which I have discussed multiple times. Now, coming on to the idea of what is machine learning. Now, we will try to generate an intuition of how machine learning works. What is it exactly? In a very lame language, you can say it is about just getting computers to learn patterns from data to predict or decide without explicitly being programmed for something. Like as simple as application of these type of things where we have to write some if-else condition. Computer is being given an example of age, salary, and credit, and based on the data, it will decide, or you can say formulate these rules automatically. Here we don't code the logic, we just supply data. Algorithm, whatever we are using, infers these logic accordingly. So machine learning is just about passing the data and picking up a model where the model tries to learn the patterns, or you can say conditions from the data, and applies it on the data which we will be passing in the future to make decisions or predictions. A formal, or you can say sophisticated definition is it is a subset of artificial intelligence. Algorithms are some of the so algorithms are used to analyze data, pattern learning, relationships between them, and generalization of these patterns are done based on the learning of rules to make predictions on the new unseen data. This definition has been, of course, referenced from Wikipedia. And key phrases here again is it is being the patterns or conditions are being learned from data. Improve with experience means you try to incorporate some feedback loop where data are being checked properly and passed on to the model where model again learns it, you can say learns in a more accurate fashion. Explicit rules are not written. Generalization is done for the unseen data. Simplest example which you will, I would say, solve whenever you are learning about the machine learning is house price prediction, where the size of the house is given in square feet, age, location, price, and all. And note that we don't pass the location as words. We pass it as numbers which the computer can easily understand. So the conversion of these type of things into, like you learned earlier, that word to number can be done from embedding. But when it comes to only categorically defining the data and not rather inferencing some of the meanings, like word here is only an location, or you can say address of that house. So here we just want it to be a particular locality present throughout the map, like this locality 1, locality 2, or I am just trying to say that you can just label these localities as a number. And it's not like some locality is greater than this or lesser than this, since these type of localities are not compared, or we cannot localities, you can say, I will write it. Localities don't capture something semantic. So, yeah, that's why we use the, you can say, location as some number-based indexes. Again, there are and this process again is called as encoding the data. And encoding is done just to categorize the data. And clearly, our goal here is to learn a function that, based on these features, predicts the price of our house. Algorithms clearly start with some rough guess for prediction. Prediction is compared with the price which we have already present in our data. Parameters are adjusted according to the actual price minus predicted price. Actual and predicted are compared to just see how far away is the prediction from our actual data. And these are repeated over many examples. Here is an example of simple linear regression. The function might look like y is equal to some weighted average of size, age, location, score, and a bias term, as you might know from basic algebra or slope line equation y is equal to mx plus c. M and c are parameters which are tuned by our machine learning model. Instead of just a single variable, it is taking into account the multiple variables. The same idea scales for far more complex models. Like there also internal parameters are adjusted. Comparison is done based on the relevant loss. Matlab, these type of thing we say as the loss function. Loss functions. There are various loss functions presented for various algorithms. Parameters adjusted so that it matches the data as well as possible. And now coming to the ML pipeline as to what actually happens in the machine learning. We say we train a model, we do the following: data. We collect the data relevant for my task like spam identification in images, sensor readings, any type of data you can say. Then these are converted into numerical features either with the help of embedding, encoding, or anything. There is a very good article written in Data Camp, like it shows us how the features are converted into relevant numerical ones. And I would say that data and data extraction, matlab data pre-processing or extraction. Pre-processing is done after we extract the relevant data. Pre-processing and extraction. Then features are engineered accordingly, like based on the data. If you feel like you can explicitly pass some data which has more relevance, like some combination of data is presenting you with the more information on lesser number of features to be used. Like supposing there are n features, some x1 and x2 feature is there. And based on some function of x1, x2, you basically manually try to guess this function or estimate it using your domain knowledge. And again, based on this domain knowledge, you try to combine two of the existing features to create this, and you can then discard these features to account for more of the s- discrete features which tries to learn more aspects of the data, since these two data points become redundant by using this function itself. Then again, after doing data, and I would clearly say that these two things account for almost 80% of our ML pipeline, because data needed should be as good as our problem statement to be solved. If data collected is different and then our model is doing predicting something else and it does not align with our problem statement, then entire pipeline or you can say effort is wasted. So it's really important that you collect the data according to your use case, according to your use case. Like for the practice purposes, we have some already available data sets. But whenever you are learning machine learning or trying to build some models around it, you might encounter the scenario where you will have to generate your own data set to solve a particular problem. So data should align with your use case or problem statement. And again, features come from the domain knowledge. Maybe you can seek some expert in that domain or try to search it out yourself. Then model comes out to be again good choice as to what model to be taken. Like linear model should suffice or decision tree, neural network. These are again some kinds of model which I will discuss later in this presentation. Again, these are parameterized function where weights are tunable indeed. Then once you select a model, training or learning occurs based on the data you provide. In each case, model predicts output, compares the prediction and true level. Then optimization are done to adjust parameters to reduce error. Reduce error, or you can say loss is reduced during training. Then evaluation is done on unseen data clearly to see how well it generalizes. Final and after the evaluation is passed, we use it to predict things in our daily life and we deploy it as a kind of working model. And you can see here, it's not just a single algorithm, it's a pipeline where we work with data, do some feature engineering, model is carefully selected, training is done, evaluation is done, and finally we deploy it to our prediction stage. Then the question answered is what exactly is learned from the data? It understands correlations within the data, like input patterns which are aligning with the output, how strongly each feature influences the prediction, like W1x1 plus. Matlab, one of the simplest models is linear regression thing, WNXN. Like there are n features, each of these features are having some data points, and for data points, if the weight of this point is higher, it implies Xn is influencing our output in a more drastic manner. And again, decision boundaries come in use when you are using decision trees or some similar algorithm, primarily for classification task where we have to separate classes in feature space. Like in any decision region, some points lying here, some points are lying here, and this is called as decision boundary. I can say it in a as lame language as possible. An example here again consists of spam filter that learns certain words, patterns, sender behaviors associated with spam and not spam. Then again, we go on to the types of machine learning. These three you will see primarily in use everywhere, like learning from labeled examples, regression type things where we have a label, matlab, we have actual label given, we have been given data points for regression classification. In unsupervised, you cannot have labels. You just have to identify the cluster of data within the space to identify similar items. Like here, one of the key use cases for clustering is customer segmentation based on their behavior. Like in a entire behavior space, some n-dimensional feature will be there where based on the all the features, some segments or clusters will be formed, which are again trying to show you how these clusters or group of users are behaving. Anomaly detection also comes under this point, trying to find unusual points. Then a third type of paradigm way of machine learning is reinforcement learning, where clearly we don't have any data like this. Agent chooses action based on the action environment responds with a new state and reward. And whenever we leave the agent in a free environment where it can do mistakes, it will learn over time a policy as in mapping from states to good actions. Good actions again are the things which maximizes our long-term reward. These type of things are used in game playing AI like chess or Go is a Chinese game, robotics. Like we cannot pass some fixed set of data to just have robot learn out of the limited data which we are passing. It is up to robot how it collides with the object or wall, how it falls, and whenever it falls, a negative term is associated with it so that internally it knows how can we, you can say, how can we improve our way of walking and all better. This reinforcement learning examples you can also see in day-to-day lives, like if a child tries to walk by itself, it will first fall very likely. And whenever it falls, a negative reward, or you can say pain is associated. Like whenever he falls somewhere, he gets hit by an object and he sees that as a negative emotion or negative experience. And the next time he internally tries to avoid that type of walking style or that type of thing so that he does not fall at least. And you can clearly see it as a trial and error learning experience where multiple feedbacks are given to it instead of labeled examples. And I have been emphasizing it multiple times that it is just used for our generalization purpose. True test of ML against is now how not how well it fits the training data. It is on how well it performs on unseen data. Like if a data is too simple, it underfits. We say it to be a high bias model. Why high bias? Because the model is biased towards a particular trend and it is missing on the important patterns. If the model is too complex, it overfits the data and memorizes noise, as in like some of the data points, I can say that as simple as matlab, like these this thing can go like this. It is able to generalize the data very well, but if some noise appears in the data, like it goes from the general trend somewhere up and down. In the case of overfitting, it will try to match all the points like this in a zigzag haphazard manner. And again, whenever a new data point appears, it will just predict very badly. You can see that this simpler one is also simpler parabola type thing is also able to predict very well. So again, we try to find the sweet spot where model captures the true pattern and ignores the random noises which appears many a times in collection of data. And generalization is what makes the ML model useful in real world. And again, why ML used instead of plain rules? Rules are too complex to manually specify in case of complex data of image, speech, and languages. Environment keeps changing and we cannot write rules for every constantly changing environment. You have lots of historical data available that contains the pattern. And ML again shines in complex things as I have discussed in the applications, image recognition, speech recognition, natural language understanding, recommendations. These are too complex to be written by someone as a hand-based rule. Again, this is just an example that there is no single way that you can write in an image that this is dog and this is cat and something like that. ML handles all this complexity. And again, complex as well as dynamic environment happens. Fraud patterns, as I have said earlier, that hackers or fraudsters are continuously trying to find out so many new ways to just do fraud, and hence it becomes a very dynamic environment and you cannot just keep writing rules for every dynamic thing. And here ML models can be retrained again on the fresh data so that the behavior involves continuously with the environment. And again, too large a scale data is, then we cannot write everything for a particular user. A generic ML model will try to identify the key features accordingly and suggest the user, or rather how it can act on a particular event. And now coming on to the myths of MLS2, how the normal public perceives these machine learning things, and you should just be aware that at the back of the magic, it's just that we are feeding the data into the system, and system mysteriously recognizes faces, write codes, and detects fraud. This mystery is associated with many of the newcomers, which sees these ML as a, you can say, something where we just pass the data and everything will happen with the machine learning. That notion is completely wrong. You have to statistically select the model accordingly, and you also have to apply some of the optimization techniques at a large scale of data so that you can get the best model for your use case. Clearly, models don't understand the world as you do. They find patterns and minimize some loss function. And again, minimization is involved with the problem of optimization. And here, the notion again that you pass whatever data you have and you will get a desired output is completely wrong. If you have not worked on data and the data is biased in some sense, incomplete, noisy, the model will tend to learn those flaws and it will rather amplify them. And you can see that ML consequently cannot fix a bad or ill-defined problem. It cannot create something completely new that is not in the data. And it will not guarantee you 100% accuracy, of course. Then coming on to the second myth is that some of the people are always fascinated by deep learning algorithms like LSTM, you can say CNN, RNNs, and all these things. Note that these type of deep learning algorithms are not always used for, you can say, every use case. It's something simple to say like you have a nail, you have hammer, and you have a very large bulldozer. It's not like that you will just use a bulldozer to nail a hammer onto a wall. Very likely it might do also, but you can see the type of uh, analogy which fits here. Even the classical ML models can solve some of your problems. It's not that you just have to keep using deep learning models every time. Using classical models of linear regression decision trees can also give you a rather better results than deep learning models. You can say you can just see it as a heuristic where deep learning can shine, where you have unstructured data, images, audio, text, and all are there. In classical ML, typically the requirement that is that the data should be somewhat tabular and you have some of the matlab, labels on which you have to work upon. Deep learning shines on these type of tasks. Data sets are massive. Data is not structured rather. And again, it's written here also that small, medium structured data set, well regularized logistic regression, tree ensemble. Ensemble is just a concept of combining multiple decision trees in the use case. It will clearly beat a natural neural net model. Or myth again here is that you should always try to learn classical models, build some applications, or rather try solving some already solved problems which can be solved by classical MLs. You can clearly find a lot on Kaggle. And once you are familiar with these classical ML models, then only you should move to deep learning models so that you can understand where we can really use the deep learning models. You will learn all those things which we have discussed, like data pre-processing and all. when you solve these classical ML problems. And some of these knowledge can also be transferred to your deep learning module, where here also you have to choose to pre-process data, choose the quality of data and all. And myth three again, as I have discussed indirectly, that it's not just importing libraries that you in a Python or any programming language, import some classifier thing and fit the data. It is only the 5% of the job. Hard 95% is everything like problem framing. What exactly are you predicting? For whom are you predicting? What is a good prediction in your sense? At what horizon, or you can say at what threshold you can say something to be a good prediction. Data quality again matters, as I have been emphasizing repeatedly, that handling missing values, outliers, noise. Data leakage refers to just you can say the ML model which should not know the data beforehand. Like I can say that whenever you are building something predictive, and in the you will be having a predicted one, predicted level or value, and actual level. During training, it's fine that you have the actual level, but during testing, you must make sure that the actual level is not present. Otherwise, it will just accidentally take that value and give you the same predicted as the actual one. Data leakage is basically the phenomena where we pass into the model some data which it should not have seen while predicting. Clearly, during prediction, you will not use the actual data. You will only work on the X features which you are working upon. Again, feature engineering is something like we turn raw data into some meaningful signals. Again, it comes from the domain knowledge, encoding categoricals. I have explained it in the house pricing thing. Normalizing is a method where we can reduce, or you can say make the scale of data uniform. In most of the cases, you will see that in optimization problems, if the scale of data is uneven, even though gradient descent and the loss reduction methods will work, but you have to do a lot of iterations and all to just arrive at a particular optimal sweet spot. Normalizing the data just tries to make this process faster. As the scale of the data is even, it will just do its work in the fewer iterations itself. And here again, you can see a model trained on dirty or mislevel data with a bad train test split is an ML model, but it is practically useless. Libraries, tools, and judgment around data all lies within your hand. Well, how are you going to predict the, matlab, how are you going to use the model, what data you need, what metrics are really needed to explain it to any user or your customer that yes, this model is able to perform these things, and so that the listener can also understand that the model is worth considering. Again, one of the, you can say, most common myth is that ML is just about gaining a higher accuracy. Beginners love accuracy because it's simple, but I would say that it is clearly misleading, especially on imbalanced data set. Like fraud does not happen, you can say, in 100 transactions. It's not like that you will be having a fraud of, you can say, 50 times. Like out of 100, 50 frauds does not occur. Even I would say in thousands of, 10 thousands of transaction, hardly one or two fraud occurs. You can say that when you are not looking into the models and data carefully, and you directly pass this data set into the model, it will just try to like if I am labeling fraud, not fraud as 0 and fraud as 1. So even if there are some of the, you can say, fraud happening inside, it will just predict everything as non-fraud. Why? Because in the data set, it has only seen that there are most of the points of non-fraud. And even in this scenario, you will see that the accuracy is high as 99%, which is not required by us because we want to check upon those only 0.5% or very few percentages of fraud. So accuracy clearly is not a metric which we would like to look in these cases. You can see here also it's mentioning the similar thing. 0.5% of transactions are fraudulent. Model predicts the same for every transaction. Looks amazing, but it does not catch any of the fraud which is occurring. In medical diagnosis also, missing a rare but deadly disease is far worse than a few false alarms. I mean, if someone is being labeled as a disease positive case and if he is not having disease, then it's fine. I mean, human's life is saved. But if the disease catching is not happening, like false negative refers to labeling something as negative while actually it should have been positive. So if it's a disease happening to a person and the person, some model is saying that the person is not having disease and it's, if it's deadly, then it costs clearly the human lives. And of course, these type of things as to how many false negatives or false positives we have to tolerate in our use case depends on the problems which we are solving. And again, apart from accuracy in these type of classification tasks, we measure some of the metrics of recall, precision, and F1 score. These are some of the scores which help us determine what threshold or what parameters inside the model can help us design our classification model. Even beyond metrics, success is not that high test accuracy. Success refers to solving the problem for the business, acceptable trade-off between the false positive and false negative. For robustness is the criteria. It should not be like just a clean prediction happening every time. 99% accurate model will not achieve anything that misses every cancer case. Now, again, these were some of the myths, and building on top of the myths, we will clearly see that some of the common beginner mistakes are they often skip statistics and probability. Note that these things are really useful to for you to judge as to what model is performing better out of the number of models you tried and tested, which model is performing really well. Some basic algorithm studying, like I always stated that machine learning is not deep learning. Deep learning is just a, you can say, subset of machine learning. So you should first clearly know the basics of machine learning. They jump directly into CNN and some fancy architectures because they are hyped or look cool, but that's not the case. Result often occurs that you tend to overfit, where overfitting is a phenomena I described earlier of high variance, where every even the basic noise is just captured, while it should have been a linear trend. Due to the noise, it captures just this complex curve. So overfitting refers to this type of phenomena, overfitting or high variance. Then again, to train this deep neural network, you will be needing a huge training time and complexity. And deep learning models are not that intuitive, though you can build some of the layers, networks, or nodes around it. But on the outer level, you cannot know what these nodes are exactly learning. It is again a matter of research which is happening even now, that how these deep learning algorithms work, how these are able to capture the data, what it exactly captures for a particular data set. It deep learning is just kind of a black box model, you can say. to solve a particular use case, to solve a particular use case. And then ignoring data quality again. If your data is inconsistent, biased, then it can cripple any model. Data is the most important thing before even thinking about the model. Data quality issues, some of the commons are missing data values, handled by dropping rows blindly. Blindly dropping rows is not a solution because if one point is missing, maybe we can try to find out that point. If that row is representing something information like there is a missing data for our cancer patient, its label is one, but its some of the features are missing. So you can clearly not afford to just drop that data blindly because you already have an underrepresentation of that data, and dropping those is not a viable solution. Then noisy annotations or wrong ground truth is again a problem. This again comes from the expertise of how you are tackling the problem. You understand the problem well enough, and your intuition or expert's intuition is saying that based on some features the label should be this, but it is labeling like this. Then again it is a wrong scenario. Duplicate records and distribution shift. This is again a complex topic, and if you know statistics, then you will understand that data tend to follow some distributions. This is one of the most popular distribution known as normal distribution. There are various other distributions in statistics and are rather used in machine learning also. So it would be better that you explore this distribution thing on your own, as it will make the video too long. And again, the effects of poor data quality is that models overfit to noise and don't generalize. Correlations are again wild between the prediction and the features. Bias happens in the data. And best practices again, you should understand how data is behaving. You should not obsess for any model architecture. You should work on data rigorously enough. See, many industry guidelines also explicitly recommend to build this robust data quality. And again, obsessing over the algorithms instead of problem framing as to what you are trying to solve, what kind of data is needed. You should not just keep hours debating on model, like predicting churn without agreeing on what churn means. Churn as in if a user is not active for 30 days, 90 days, or if he or she is unsubscribed. You should understand the problem good enough. These are some other use cases also: predicting fraud without clear labeling and business feedback, recommendation system without defining what counts exactly as a good recommendation. Algorithm choice will not matter if it is not answering the question correctly. Good ML clearly will start with so asking these questions: who will use this? How the model output will support the decision? Cost of false positive and false negative? What are the simple baselines which are existing already that I need to pick up? Only then clearly you will pick and fine tune the algorithms accordingly. And some of the key takeaways are: repeating is that good problem, like you should have a good idea of how the problem is working, what problem you are solving. Defined target should be there, constraints should be understood by you, and success, how do you define the success associated with the real world? Good data is important to solve this problem. Clean, representative, well labeled, monitored for quality issues. It should be monitored continuously, and a reasonable model. Of course, we will start with simpler models with appropriate metrics and only increase the complexity gradually when the problem and data justify it. I mean, if you have worked on data, you know that the data is good enough, problem is clear, then only you will increase the complexity for the models accordingly. So yeah, that was a brief introduction of how you can use machine learning, what problem it tries to solve, what are the general tactics to approach any problem which can be solved using machine learning. So that was from my side. Thanks to you all.